Imagine you wanted to know the area under a complicated curve, like the probability that a stock return falls within a certain range, and calculating it directly may be impossible, but statistics gives us a clear way. We can estimate it using random samples, and that's the idea behind numerical integration, the statistical way. Hi, I'm Professor K. Muralidharan, a Six Sigma consultant and a quality trainer currently working with MS University of Baroda. In this video, I will show you how statistical simulation approach can be used to approximate numerical integration of mathematical functions. So what is numerical integration? It's a computational method used to approximate the value of a definite integral when it cannot be solved exactly or analytically. Of course, it's a field generally discussed in mathematics. So in almost all fields of mathematics, you can see numerical integration comes in. So in physics, engineering concepts, in statistics, of course, we can even simplify many of our computational probabilities using numerical integration. Machine learning is the new generation technology. A lot of cases and contexts you can see where numerical integration is used. Of course, that is generally in the Bayesian inference part, because most of the time Bayesian inference, you cannot express the likelihood in a closed form expressions, and so we have to approximate using numerical integration. Okay. So what is numerical integration? Let us say we wanted to compute the integral a to b y dx. Very simple, general format. Okay, you can use very well the numerical mathematical way of doing it. So finite difference method, a lot of ways you can try. Trapezoidal rule, Simpson's one-third rule, third rule, 3 by 8 rule, etc., etc. You might have studied a lot of such tools. So it's a standard result. Integral a to b y dx can be approximated as nh times y naught plus n by 2 delta y naught plus n 2 times 2n minus 3 by 12 delta square y naught plus etc. So you can refer to some numerical integration books and you can see that result. It's a very famous and generally used. Okay, and where a and b is approximate, a is actually x naught and b is your x naught plus nh x. So in a short, you can make any number of integrals. So h is the interval of difference in here. Okay, so for various values of n equal to 1, 2, 3, etc. So for 1 it becomes the trapezoidal rule, and 2 it becomes the Simpson's one-third rule, etc., etc. Okay, so let us see. We wanted to compute integral 0 to 1 by 1 plus x dx. Okay, so the exact value is log 2. So you can very well, it's a standard result, and the value is 0.69317. If you use those formula which is shown previously, using various values of n 1, 2, 3 like that, you can get the approximation. So trapezoidal rule gives 0.6941, and you can see all other lot of formulas and values. Simply by substitution you can get. Okay, and you can approximation can be improved further by giving the interval of differencing the way you make the choice for the interval of differencing here. Okay, so let us now talk about the statistical simulation of integral a to b y dx. Okay, and this is the purpose. So how we can do it? Not using exactly mathematical techniques, but using statistical principles. Okay, so later on I will show you how in various examples by changing a and b. Say for example a is 0, b 1, so it's integral 0 to 1 y dx. Then we'll talk about integral 0 to infinity y dx. Then we can also talk about minus infinity to infinity and y ds, etc. Okay. Suppose we wanted to find the integral of a to b y ds. So what you need to do is simply bring in some density function inside the integral. Okay. So look at this integral y, that y dx, that y function is completely converted into a form gx into f of x, and f of x is the probability density function. Okay, that could be the statistical portion. You can say the main importance is coming from through that. So if f of x is the density function, so you can write integral a to be a gx f of dx f of x dx as expected value of gx. It is simply the average of gx. Okay, so it's simple. The procedure is you generate samples from f of x. If you know fx, so it can be exponential, any distribution, variable, or it can be beta, uniform, Okay, so you know how to generate samples, or else you can take the help of software programs like R programming, Python language, or even Minitabs, SPSS, etc. A lot of random number generators are available these days. Okay, so that's not a big deal. So generating samples from f of x can be done easily. Then you compute the function g of x. Okay, so that g of x. So x is the sample which is coming from the density function. Okay, so then based on that you compute the g of x, then take the average of x. So a very simple procedure. Okay. Okay, let us look at the simulation of a to b integral a to b dx, where gx is 1 by 1 plus x. We have already done it using the mathematical integration. So we got the values almost all approximated to 0.69 something. So you can see that here I have used f of x as using the same principle as shown in the previous slide. So we have shown that the integral is expressed as gx into f of x. Fx we are assuming it as u01. In that case, I am getting the value 0.6942. Beta 22 is another integral. The reason why we have selected beta 22 or beta 23 is because the random variable takes the value from 0 to 1. So that is the idea behind it. So you have to suitably decide which distribution fits well and where. Okay, and the uniform A to B can be generated with the following way: x is equal to a plus b minus a times u. Okay, in the same way, very simple calculation, say the simple way you can do it. In the same way, you can calculate, say for example, 0 to 1, integral 0 to 1 is root of 1 minus x squared dx as 0.7853, and 0 to 1 sine of pi x, using this similar statistical ways. Okay, please, I request the audience to try this, whether you are getting the same answer. Approximation, there can be some approximation, there can be some value, approximation in the third digit or fourth digit. It's many often it happens, because what you need to do is you can improve always the accuracy by increasing the sample size. Okay, let us look at the integral a to b, where a is 3 and b is 7. So integral 3 to 7, 1 by 1 plus x dx. Okay, you can always get the value that log 1 plus x to the limit to 3 to 7. You can compute the actual value also. Okay, so the actual value is log 8 minus log 4, so 0.6931. So let us look at the whole procedure. So what I did was I simply multiplied and divided by 4 by 4, because the ratio, the difference is 4. So 4 by 4, that is the idea here. So 1 by 4, you can see I take it as the uniform distribution. Okay, so now I have the expected value of gx. Gx is actually 4 by 1 plus x, and f of x is your uniform 3 to 7. So what I did was, the right side you can see the calculations done in the Excel software. Very easily you can do it in Excel software. I generated the sample from uniform 3 to 7, that I call it as x variable. And then gx is computed 4 by 1 plus x, and take the average of gx. That is what is shown as 0.6919. You can see that how it matches with the actual value. Okay. Here is the simulation of integral 0 to infinity g of x dx. Okay, let us say gx is x square e power minus x. So I is actually integral 0 to infinity x square e power minus x dx. So I am converting that as ux into f of x dx. So that becomes at finally expected value of ux, where ux is actually x square and f of x is e power minus. I suitably selected or chose, or I separated out the density function. So it becomes the unit exponential distribution. So here is the whole calculation. So what I did was, for generating uniform exponential, you need a uniform sample. So uniform 0, 1 sample is generated first, then x is generated from the unit exponential, and then computed the function ux is equal to x square, and take the average of that. That is coming out to be 1.987. Okay, and actually the value is gamma 3. We say gamma integral. If you see integral 0 to infinity x square e power minus x dx, it is actually gamma 3. So gamma 3 means it's 2. So you can see how statistically, through statistical approximation or expectation way, how much we got the value. So it's the difference is so short. So much is giving much. So you can improve the accuracy by increasing the sample size. I considered around 10,000 samples. So you can increase to 1 lakh, more numbers. So the more, the better. So the accuracy improves. So let's look at another function, gx is equal to x cube e power minus 2x. So here I suitably did a multiply divided by 2, so that I can make it as exponential distribution with parameter 2. Okay, so mean is 1 by 2 in that case. So the whole integral is expressed as integral 0 to infinity ux f of x dx, where ux is actually x cubed by 2 and f of x is 2 e power minus 2x. You can get the value I is equal to 0.389. Okay, same way you generate uniform 0 1 if necessary. For SPSS and this thing, you can directly get the samples from exponential distribution. You don't have to go for a uniform 0 1 random variable construction. So you can get it and take the average of that ux. So computational ux actually depends on the density function. Okay, so please make sure that it is done properly. Okay, so the actual value of the integral is gamma 4 divided by 2. It's again a gamma integral. So gamma 4 divided by 2 raised to 4, that is 0.375. So the approximate the value we are getting is 0.389, slightly more than that. So again, more and less is always possible accuracy. If you want that this value is not okay, then you can increase the sample size, definitely, which is always increase the sample size. Definitely you can improve and you can approximate with the actual value with less number of error. Okay, here is so in general 0 to infinity gx dx. So gx is this is a complex function. So this integral may not be known. Yes, this is integral is also known. So the actual value of the integral is pi times log 2. So that is 2.1773. Okay, so let's see how we could make it the statistical simulation. Okay, so it is again expressed. So what I did was I multiplied divided by a density function f of x divided by f of x. So the whole ux become now the 1 by 1 plus x square log x plus 1 by x divided by f of x, and f of x can be any density function defined in the interval 0 to infinity. So you have now a lot of choices for the density function. There are many probability density functions which are defined in the interval 0 to infinity. So you have now a plenty of choices. So try with all types of this thing. So I will show you how I have chosen. So I took exponential 2 as the base distribution here. So the whole integral is computed. So the whole process is also shown here. You can see the average is coming out to be 2.163, which is actually the last column average. Okay, so the whole computation is shown here. This is actually an Excel computation. One can very easily work with, because if you don't have any other software, and then if you are not familiar with any other software, you may have some problems. So Excel software based computation is shown here. Okay, so one should also see that so the actual value is also matching with that the numerical integration, the statistical way also. So what is the takeaway? So the Monte Carlo integration uses random sampling to estimate integrals, especially useful in high dimensions where traditional methods fail. And the accuracy of the estimate provides as the number of sample size increases thanks to law of large numbers, because we have learned and we discussed a lot of law of large numbers in the statistics class. So many often you can go for the convergence with respect to various quantities. So see whether it applies or not. And most of the even we have central limit theorem also works well. So there is no an issue, and more the better, because sample size increases always. It's we are moving towards the population, so definitely the accuracy will definitely improve. And the approach is flexible, widely applicable, and underpins methods in simulation, finance, physics, and machine learning. Almost all application areas you can see we can very well use with all trust in the method. And statistics provides a practical and powerful toolkit to solve integration problems that pure calculus alone cannot handle. That is always possible. If you look at many complex integrals, you always get an approximate formula. There is no compact value which is discussed. So that can be handled, very well handled with statistical way. Okay, thank you very much. Stay tuned for further videos, and it's going to come up very soon. Thank you very much.